Well, good afternoon, everyone, and welcome to the fourth and last in our series of webinars on climate science, informing adaptation and resilience to climate change. This is hosted jointly by the CIWEM Presidential Team and also the British Hydrological Society. And just a bit of a housekeeping to begin with. This webinar is going to be recorded. We'll only share it on the CIWEM website as long as we have permission from all the speakers to do so. If you have any problems with hearing or visual aspects, then use the chat feature on Zoom to let us know what the problem is. If you have technical questions about the speakers, then please use the Q&A. And we'll take all questions at the end of the presentation. And this webinar counts for 1 hour of CPD. So before we get on to today's topic and the speakers, just a few introductions. I'm Duncan Faulkner, President of the British Hydrological Society, and I'll hand over to Hannah to introduce herself.
Thank you, Duncan, and good afternoon, everybody. I'm Hannah Burgess, and I am the CIWEM President.
And then also on the call we have Peter Rook, who's the Junior Vice President of CIWEM, and he's going to be organising the questions at the end. So a little bit about CIWEM. If you're not already familiar with it, you can find out a lot on the website and also information about how to join. And similarly with BHS, British Hydrological Society. So today's topic then, we've covered through this series, first of all, introduction to the latest climate science and the process of getting from climate models into the information that practitioners need. We've then focused on flooding, on water resources, and today's webinar, last but very much not least, is about water quality. So the impact of our changing climate on the physical, chemical and biological quality of our environment. And I will stop sharing now and introduce the first speakers as they begin to share their screens. So we've got a joint presentation, first of all, from Elliot Gill of Stantec and Murray Dale of JBA. Elliot is a CIWEM fellow with over 30 years of experience in the planning and management of urban drainage systems, and he's a senior technical director at Stantec and also the past chair of CIWEM's urban drainage group. And in recent years, both Elliot and Murray have been focusing on the major programs of investment in stormwater overflows to protect river and sea water quality. Murray then is a chartered meteorologist with a similar length of experience in water management and hydrometeorology. Murray's been working with UK climate projections since 1999, and he's led teams that have developed the REDUP tool, which I think he's going to be mentioning today, which produces synthetic rainfall data to allow water and sewerage companies to plan for the future. And Elliot and Murray have worked together on and off for about 25 years, developing the science of using rainfall data in urban drainage systems. So over to Elliot.
Thank you, Duncan, and good morning, everyone. I'm really delighted to be speaking to you this morning. So broadly, the content today is about water quality, but specifically, I'm going to be talking about how our urban drainage and wastewater systems affect the quality of rivers and seas, and then even in more detail, how storm overflows affect that water quality and how we are using climate science to understand the future performance of these overflows, and then how we're planning and designing for the future with that information. So Murray and I are going to do a double act on that. So maybe you've been under a rock and you don't know what a storm overflow is, but I think this diagram really helps. So in dry weather, sewers work normally, everything gets transferred to a treatment plant. But when it rains, because all the rainwater enters the same piped network, that is quickly reaches its capacity, and we get these discharges of dilute but untreated wastewater into receiving waters. So the clue here is in the rainfall, and understanding the current and future patterns of that rainfall help us understand the dynamics of this system and help us to design solutions to make them work better in the future. So there are more than 20,000 storm overflows across the United Kingdom. They are, everywhere. A real kind of legacy of when our drainage systems were first developed in the 19th century, largely. And a slightly, different pattern and intensity of them in the different UK countries of England, Wales, Scotland, and Northern Ireland, and slightly different policy and regulatory rules apply in each territory. So forgive me if I don't go into all of that just now. So what's causing a lot of excitement at the moment is we're at the cusp of an incredible capital investment in England and Wales, certainly. We're about to enter on the 1st of April the AMP8 period. And on storm overflows, we're looking to spend around £11 billion improving these overflows and continue at a broadly equivalent rate all the way through to 2050. So compared to the history of investment, certainly over the last 20 years, this is a huge step change in investment and improvement. And the requirements in England, at least, where most of the overflows are quite simple, really. In the future, these storm overflows must cause no environmental harm, so no water quality damage must be caused by them. And on top of that, a requirement that they discharge fewer than 10 times per year on average. So when we design, we need to plan for the future. We need to consider what the future climate will be and make sure that these overflows only discharge up to a maximum of 10 times per year on average. And in total, through to 2050, this is around a £70 billion program of improvements. So it's a really radical change in how much attention we're giving to these drainage systems, which have probably been a little overlooked in previous decades. This diagram is quite interesting. It shows you the average number of spills per overflow by year and then by water company as well. So you can see at the moment, the average number of spills per overflow is well above 20, often in excess of 30 or 40 spills per year. By 2050, that average will be fewer than 10. 10's the maximum, but some don't spill that anyway. So the average by 2050 will be fewer than 10 spills a year. You can see year to year as well a great deal of variability, and that's just because of how the weather changes year to year. We have dry years and wetter years, and certainly in wetter years, and 23 was a wetter year, you can see how the average spill count is a lot higher. 2024, I think, is even wetter again. We don't have the data for that yet. So just a little diagram here that explains how we kind of plan and design in this space. And those cogs and gears in the middle represent the hydraulic and water quality models that we use to do this. So when we plan for the future, we need to look at 2050, and there's various uncertainties and input variables we need to change. There's the number of people. There's the degree of what we call urban creep in our cities, i.e., how many front gardens are now paved over so people can park their cars on them. The water consumption of those people, because that affects how much wastewater they generate. And critically, rainfall. So rainfall is used to drive the sewer models that tell us how much spill occurs, but they also drive river models about the quantity of water in our rivers, and also temperature. What's the future water temperature? Both of those factors are important, the quantity and temperature of water quality. And then on the right-hand side, this modeling environment throws out lots of information data on the frequency of these spills, and also the state of the water environment, the water quality in the environment. And then engineers and planners then propose and develop and test solutions to bring this system into spec to meet the new requirements of no environmental harm. So you can see, I think, how important the rainfall variable is here. There's considerable uncertainty about what it might look like in the future. There's a year-to-year variability at the moment. So both of these things mean that we've had to develop a new set of tools and processes to help us model rainfall for now and the future. So with that very brief introduction, I'll pass on to Murray.
Thank you very much, Elliot. It was very helpful. I'm Murray Dale, a hydrometeorologist. I'm a technical director at JBA Consulting, and I'm going to talk about a climate service or a tool which has been developed to address these issues that Elliot's been talking about in ways we can manage the rainfall that is falling at the moment, but also what we think is projected for the future. So a key element of this is the intensity of rainfall. It's not so much necessarily the total rainfall that's falling in any one period. It's how heavily that rain is falling and over what extents. So we refer to this rainfall rate as intensity. So it's the rainfall intensity we're trying to get a handle on and understand for the future. Next slide. And to drive this intensity, there's the process of convection in the atmosphere. So you may remember, if you've studied geography or meteorology, that there are different processes that produce rainfall in the UK, frontal rain, orographic rain, etc. Convective rain requires heating of the land surface. So typically this convection occurs in the warmer months in the UK, but it's not exclusive to that. And we have noticed periods of pockets of convection occurring within frontal systems at all times of the year. But understanding these convective processes is not straightforward. They are relatively small spatially. They can drop very high rates of rainfall in localized areas, which where it can even be dry in next door to that, especially in the summer months. But rainfall intensity is not spatially consistent. It's highly variable. Next slide. So in order to try to address this issue and look towards the future, we can benefit from some really cutting edge science from the Met Office, who have led in many ways globally, led the way in developing nationally developed climate models that are called convection permitting. So that means they can operate at spatial resolutions which are fine enough to resolve convection explicitly. And that means they are a step change away from sort of regional and global models, which use other processes or other methodologies to estimate rainfall and often don't capture well the high intensities and the variation in intensities in rainfall. So since 2017, we've been making use of this climate modelling from the Met Office. They've had convection permitting modelling since 2014-15 in an experimental model earlier on. And we've done this work for UCWER, UK Water Industry Research. So I'm grateful to them and acknowledge the input of UCWER for this work that I'm describing now. In 2018, or in fact, I think it was 2019 when this particular product was released, there is a 2.2 kilometre ensemble called UKCP Local. And this has multiple members in it. So that means it's been simulated 12 times to give some degree of uncertainty. It's nested within regional climate models. And if you advance a couple of times, Elliot, the data are now available for 100 years, whereas it was available for 3 20-year periods before. So we've, since last year, now got 100 years of this data at hourly resolution every 2 kilometres across the country. Next slide, please. So we devised a climate service or tool called REDUP, and the reason we came up with that term is that RED stands for Rainfall Event Data Files. So there are RED files that are used within nationally available and commonly used urban drainage modelling software. And those are data files of historic rainfall data that are measured from rain gauges and can be very high resolution, down to 1 or 2 minutes. And the purpose of this tool is that it perturbs that historic rainfall data to produce an uplifted version of the data, including uplifted rainfall intensities, because we're seeing rainfall intensities increasing in the future. So that's the up part. So this is read up, and you can find it on the UCWER website, and it's available to UCWER members. Next slide. How it works, we haven't got very long here, so there are 3 elements to it, and I'll cover them brief, and if there are questions, we can address them. So it's doing 3 things. As well as increasing intensities in line with future projections of individual rainfall events, it's also carrying out a perturbation that results in similarities of number of dry days in the future. So we are facing in the future warmer weather, hotter, drier summers in general, but when it rains, we're expecting it to rain more heavily. But we want to not just, if we just increase intensities throughout, we'll end up with more rainfall in the synthetic data we're producing in the model. So we need to carry out 3 steps in the perturbation: the intensities, the dry day periods being similar, and also achieving a level of similarity in seasonal rainfall totals. So those things are done through this tool, and it then outputs some perturbed data. Thank you. So this shows an example of how the data are perturbed when you look at a time series. The benefit of this tool is it's not just uplifting a discrete individual event, like another system that was developed called Future Drainage, that was designed for flood risk in particular. This tool is perturbing a time series of data at the same resolution as which it started. So if you've got 2-minute data, it will perturb at 2 minutes. And it's making the change from top to bottom in this example by uplifting individual events. So you can see one event's been uplifted here. You can also, if you're looking closely, spot that 1 or 2 other events have been altered slightly in the remainder of the record over that month. But also that some of the rain has been removed through that process to achieve these dry day and total rainfall targets that the tool does. So that's just an example of how it's making this perturbation. Next slide, please. Final slide. This is effectively what we've done here is a co-created or co-designed climate service. So it's important that when we're developing services like this, that users of the service are involved right at the outset. They are consulted on what they want, how it should be produced, and they're involved as we develop it and reviewing its versions to help improve it all the way along. So it's a collaboration very much from its concept through to its delivery. And if you want to find out more about some guidance on climate services and helping ensure those co-design elements, co-creation are involved, there's a web link there. So finally, thank you to UCWER for funding of this REDUP service over 3 projects over the last 8 years. My colleagues at JBA, Elliot and colleagues at Stantec, colleagues from Rain++, and previously inputs from the Met Office and Newcastle University. Thanks very much.
Thank you very much to Elliot and Murray. So pop any questions for them in the Q&A and we'll deal with them all at the end of the webinar. So we're next going to hand over to Richard Pickering from Binnies, and Richard will start sharing his screen now. Richard is a technical director in the Process Technology Group at Binnies. He's a chartered chemical engineer and a member of CIWEM and Institute of Chemical Engineering, and he has over 28 years experience working as a clean water process engineer. He's worked on all aspects of water treatment, providing solutions to treat the full spectrum of raw water sources used in the UK. And he's worked on feasibility studies, outline and detailed design activities, and process commissioning. Over to Richard.
Thanks, Duncan. And good morning or afternoon, everyone. and thanks for the opportunity to present today. Topic for this presentation is the impact that climate change has on water treatment. I'll talk a little bit about what those climate changes are for the UK. I'll go on to talk about some examples of the changes they bring about to water quality in our water sources. Lastly, I'll go on and talk about the implications that these changes in water quality have for our water treatment works. Climate change effects that I'm concentrating on today come down to basically three areas. Temperatures are increasing. The 10 warmest years on record have all occurred since 2002. Summer heat waves are getting more extreme, but it's not just the summer peaks. Winter temperatures are also increasing. We know that increasing carbon dioxide in the atmosphere is a major cause of the increase in temperature, but the increasing concentration of CO2 may also directly affect water quality. Average rainfall is increasing, but alongside this, the weather patterns are changing, with the rain falling in more frequent and more intense storms through the winter and longer, drier summers. This is reflected in the Met Office climate change predictions for the UK that estimate that by 2070, winters will be up to 4.5 degrees warmer and 30% wetter, and summers will be up to 6 degrees warmer and up to 60% drier. So what impact do these changes have on water quality? Before we get to the changes in water sources, first I want to consider some of the changes that occur on the land. Higher ambient temperatures cause an increase in soil decomposition rates, leading to an increase in nitrates being released. When it rains, the water then picks up these nitrates and carries them into the watercourses. Higher temperatures and longer droughts lead to a drying out of peat moorlands, which lowers the pH as a result of increasing the concentration of humic and fulvic acids within the peat. These humic and fulvic acids are one of the main causes of colour in upland waters and contribute to natural organic matter in the water sources that has a big impact on water treatment. When it does rain, as the water passes through the peat, it picks up these more concentrated organic acid compounds, increasing the colour and lowering the pH of the water. As a result of the lower pH, there may be an increase in the dissolution of metals and other minerals on its way to the springs, streams, and rivers. As a result of the more intense storms, there's a greater risk of soil erosion, carrying away large amounts of particulate materials into the watercourses. This can cause huge increases in the amount of solids being carried into the rivers. These climate changes also have an impact on plant growth, which may in itself cause changes in water quality, but the consequence of this that I wanted to focus on is that this may then lead to reactive agricultural changes, such as the increased use of fertilizers by farmers to maintain their crop yields, which then get into the watercourses through runoff. Moving on to rivers and streams, the amount of carbon dioxide dissolved in water is in equilibrium with the concentration in the atmosphere. As the amount of carbon dioxide in the atmosphere increases, there'll be an equivalent increase in the water to maintain that equilibrium. This in turn will lead to a lowering of the pH of the water. With increased dry weather periods, we get a slowing of the flows in rivers, along with shallower depths, which makes them more prone to increasing water temperature. The reduction in flow and warmer water lead to reduced oxygenation of the water and an increased risk in stagnation. Lower river flows reduces the amount of dilution of discharges into the watercourse, such as industrial discharges, sewer outfalls, or agricultural runoff, and so may lead to increasing concentration of pollutants. Increases in the amount of carbon and nutrients in the water can lead to increase in plant growth and algal blooms. And increased rainfall and flooding causes an increase in flushing of contaminants into the watercourse, similar to erosion talked about previously, but also picking up pollution and contaminants from farmland, roads, and other hard surfaces. Lakes and reservoirs are vulnerable to the similar effects as rivers and streams. We talked about the increase in carbon dioxide and nutrient concentrations, and we talked about the effects of low flows on contamination concentrations and about storm conditions adding to the contamination. Where it differs in lakes and reservoirs is the greater retention time and dilution because of the storage volume. This attenuates sudden changes, averaging out to give lower increases, but lasting for longer periods. The longer retention time also allows for further changes within the water body. As a result of the increased carbon and nutrient concentrations, the amount of plant growth that can be supported in the reservoirs increases, and this is called eutrophication. I have come across a few upland reservoirs that historically were considered as oligotrophic lakes, where the nutrient concentrations were too low to support the growth of aquatic plants. As a result of increasing nutrient concentrations, they're becoming increasingly prone to algal blooms. Algal blooms are an issue, not only with the effects that they can have in the treatment works, but also because when they die off, as the algae cells decompose, they release taste and odour compounds, primarily geosmin and 2-methyl isoborneol, into the water, needing additional treatment to prevent customer complaints. As a result of increasing temperatures, stratification effects tend to form earlier and collapse later. These are where the lake or reservoir splits into two independent layers because of the temperature gradient from the water surface to the lake floor. The boundary layer between the two zones is called a thermocline. The upper layer receives nutrients from the incoming flows and gets warmer, which increases the risk of algal blooms. The lower layer, which is cut off from atmospheric oxygen by the thermocline, becomes anoxic, and with increased anaerobic activity and dissolution of phosphates, metals, and minerals from the sediment. This remains stable until seasonal temperature reductions cause the upper layer temperature to fall and the thermocline dissipates, and the two layers remix. With the stratification lasting longer due to climate change, there's a longer period of time for the anaerobic activity in the lower layer, increasing the amount of dissolution, whilst at the same time providing more time with a higher temperature, further increasing to the extent of algal blooms. So how do these changes influence water treatment? Increases in particulate matter, along with dissolved metals, will increase the solids load into the treatment works. These would need an increase in coagulant usage to allow the solids to be removed in the clarification and/or filtration stages. It may be necessary to upgrade these processes to cope with the increased solids load, and depending on the extent of the increases, it may also have an impact on the capacity of the sludge plant. The extent and speed of the storm peaks for particulates in river sources in particular can exceed the capability of the treatment works, causing shutdowns until river quality improves again. As a result of the changes in weather patterns, we're seeing an increase in the number and duration of work shutdowns. One mitigation for this might be bankside storage, but with the increasing frequency and intensity of storms, there's a need to give more consideration for future weather changes to determine how much storage is required and how quickly it can be replenished. There are several different types of organics that we've talked about. Increases in natural organic matter, such as humic and fulvic acids, will impact on coagulation and clarification stages. As with increased solids load, there may be a need to upgrade the treatment process or sludge plant capacity. There may be a need to consider alternative processes to improve the removal of the natural organic matter. This is particularly important because insufficient removal can lead to formation of trihalomethanes, which are carcinogens, when chlorine is added for disinfection later in the process. Activated carbon may be required for removal of some organic pollutants, such as pesticides, and increasing concentrations of those would increase the frequency of regeneration. There are lots of different types of algae. Some of them are mat-forming types that can cause blockages in channels or blind filters. Others are more filamentous that can pass through the sand filters and cause problems later in the process. Increases in algae would need an increase in coagulant dosing and again can impact on the capacity of the treatment stages. Settlement-based clarification in particular struggles with algae removal because the algae wants to float. And this can be an issue for these sites which have not historically had algae issues. Flotation-based clarification is much better suited to algae removal. In addition to dealing with the algae itself, there's likely to be an increase in the need for treatment for removal of taste and odours. The normal approach for these is to use either powdered or granular activated carbon, although in recent years, due to increasing concentrations of geosmin and especially 2-methyl-isoborneol, I've seen sites need to use both forms to remove the compounds down to an acceptable level. If levels continue to rise, it may be necessary to consider ozonation or advanced oxidation processes to ensure that they can prevent taste and odour complaints from these chemicals. Lastly, with increases in bacteriological contamination. This may involve bacteria and viruses themselves or associated compounds such as ammonia. Deterioration in bacteriological compounds may need increased disinfection capacity, while compounds such as ammonia increase the chlorine demand of the water, and so we need to dose more of the chemical to get the same chlorine residual. As we've seen across a wide range of changes in water quality due to climate change, if that's addressed at the treatment works, they'll result in the need for increased chemical usage and may also need uprated treatment processes or additional treatment stages. These additional treatment requirements would lead to increases in embedded and operational carbon. There have been some projects carried out using nature-based solutions for catchment management, such as the re-wetting of peat moorlands, that can provide more sustainable solutions. I suspect that going forwards, we're going to need a lot more of these kind of schemes to mitigate the effects of climate change. So, kind of just to wrap up, I've talked about the climate changes in the UK with increasing temperature across the seasons and drier summers and wetter winters, and also changing in the intensity and frequency of storms. The impact these climate changes has the impact of these climate changes has a range of impacts on water quality in our water sources and their surrounding catchments. This may lead to increases in suspended and dissolved solids, nutrients and organics, and other pollutants. Subsequent changes as a result of the increases in temperature and nutrients increases the amount of aquatic plant growth and algal blooms. Consequences for these on water treatment are likely to include increases in treatment capacity to deal with the increased solids load, new treatment stages where the existing processes can't treat the more challenging conditions, and an increase in chemical usage. Dealing with this deterioration of water quality at the treatment works will include increases in embedded and operational carbon. Nature-based solutions that can be used in the catchments can help with providing sustainable solutions to this challenge. That's the end of my presentation. If you have any questions, please put them in the Q&A, and I'll hand back to Duncan.
Thank you very much, Richard. That was a topic I knew so little about at the start of your talk, and I learned a lot through it, so thank you. So our final speaker for today is Tim Darlow. Tim is a chartered member of CIWEM. He's a chartered engineer and a chartered environmentalist, and he has over 15 years experience working on a range of water treatment and supply projects, including process design, water strategy, and developing approaches to assessing and managing risk across water supply systems. Over to Tim.
Thank you for your introduction, Duncan, and it's great to be speaking to everyone today. So what this talk is about is a project that was delivered jointly between a partnership between M2, JV and Scottish Water to carry out an assessment of the impact of climate change on water treatment in Scotland. I will talk about how we're already seeing changes in the quality of our water sources, and how we, in this project, developed an approach to assessing the impact of future climate change-driven changes on water treatment in Scotland. I think what we'll show is that we are making notable progress in understanding the impact or potential impact of climate change on water quality in Scotland, but that more work will be required collectively from the scientific community to enable us to fully understand this impact in the future. This presentation has been jointly prepared by myself and Stuart Sutherland and Mark Williams from Scottish Water, but I would also like to recognise the impact of the project from the people listed at the bottom of this slide. So first, I just want to talk briefly about the organisations who delivered this project. Scottish Water, as you may know, is Scotland's publicly owned water supplier, and it operates 229 water treatment works from 444 individual water sources, supplying close to 1.5 billion litres of water a day to over 2.5 million households. Water sources that supply these treatment works range from small river sources to large upland reservoirs, although by population, most of the water is served from reservoir-based sources. M Squared is a joint venture between Stantec UK and Mott MacDonald, and we provide technical consultancy services to Scottish Water. Scottish Water has made a commitment to be a net zero emissions business by 2040 and has published at the end of last year a climate change adaptation plan, which some of this work fed into. And the work I'm going to talk about has, like I said, fed into this climate change adaptation plan, and I will be focusing on the treatment elements of that. Before we started this work, it was evident that we were already seeing changes in our water quality sources. Upland reservoirs provide a substantial proportion of drinking water in the UK, and these catchments tend to be dominated by organic or peaty soils, which release organic content into the reservoir, as Richard's given us an excellent introduction to. The presence of organics in our treatment water presents challenges to process engineers, as it can overload solids removal processes and increases the risk of the formation of disinfection byproducts. And over the last few decades, we've already seen changes in quality of these sources. And if you just see the top graph here, this is a trend of dissolved organic content for Loch in the Trossachs in Scotland, which is served by, which has a catchment with a high organic soils, proportion of high organic soils. And although organic content will undergo seasonal variations, you can see here there is a definite trend in increasing levels of organic content of the water. And the upward trend that we've seen at the end of the last century has really been attributed to principally to regional scale chemical recovery of upland soils since governments in Europe tackled the impacts of acid rain. But however, organic release from these upland soils has been shown to be sensitive to temperature and the amounts of rainfall, and future warming as a result of climate change and changes in rainfall pattern is likely to increase the organic concentrations in water draining from peat catchments. And one thing to note is, of course, many of our water treatment works in the UK would have been designed and built this period here when organic levels were lower and may not be able to cope with future changes or the current changes and future changes that we're seeing in organic content. But it's not just organic content which is of concern, and Richard gave us an excellent overview of in reservoir processes, and I just want to talk about a few things specific to Scotland. So the potential for warmer summers and more variable rainfall patterns can obviously impact environmental processes in our reservoirs. And the Centre of Expertise for Waters in Scotland has identified a water temperature threshold of 17 degrees as a tipping point above which algal blooms are more likely. And they have estimated that by 2050, as a result of climate change, that most water bodies in Scotland will experience this for at least 1 month of the year. And therefore, if nutrients are available, they are at increased risk of algal blooms. Increasing temperature could also increase the risk of thermal stratification within a reservoir, which could promote release of nutrients, in particular phosphate from bottom sediments. And the combinations of nutrients and higher water temperatures could lead to greater risk of algal blooms, in particular cyanobacteria, which release unpleasant taste and odour compounds such as Josmin and MIB. And not all of Scottish Water's water treatment works were originally designed to treat high levels of algae and the taste and odour compounds that they can produce. Furthermore, an increase in thermal stratification can also release metals from sediments in reservoirs, in particular manganese, which can cause discoloration problems in downstream water networks. And as for algae, not all water treatment works are equipped to remove dissolved manganese. The goal of our project was to assess the key risks to water treatment in Scotland and identify responses for adaptation. And a key challenge that we were set was to actually try and start to quantify how the quality of our water might change. First of all, we carried out a screening risk assessment where we combined the knowledge of M² and Scottish Water and a quite extensive literature review to identify the key water challenges or the key parameters that would change under climate change scenario. And they were algae and algal taste and odor compounds, manganese, organic carbon, and turbidity. And then for each of the 229 water supply systems, we went through a process of assessing the vulnerability of the sources to climate change and compared that or aligned that with the process type, the water treatment process type that they fed and its capability to respond to changes in the raw water. And then for each each water source and treatment works combination, this enabled us to assess its vulnerability to climate change. And the outputs of this work were set out in Scottish Water's climate change adaptation plan. And the key points for that were that the majority of Scottish water sources will have a risk of deteriorating water quality. This is by 2050. 14 water treatment works would have a high vulnerability to climate change, and a further 71 water treatment works would have a medium vulnerability. And then we really embarked on a second phase of the project. So for the next phase of the project, we were set a challenge of whether we could actually quantify the change in raw water quality to the works so that we could better understand adaptation responses, and whether we could consider 2 climate change scenarios of a 2 degrees warming to 2050 and 4 degrees to 2080. So this slide presenting a summary of the methodology we developed using organic carbon as an example. And there was quite a lot of, as you imagine, complexity in the work we did, which I can't cover completely in a time of this presentation, but my aim here is just to give you an idea of the framework that we deployed. So first of all, we obviously reviewed a lot of existing literature information around existing methodologies for how we could predict future changes in raw water quality. But we couldn't really identify any methodologies that we could immediately pick up and use or really apply within the time scales of the project. So we developed this approach. And broadly speaking, we identified a set of future risk factors. So we identified what could change under climate change, what climate factors, and how they would influence our parameters that we're trying to assess. So for organic carbon, the main impacts would be from changes in rainfall and temperature. And then for each catchment, we looked at a set of catchment and source characteristics that might make that source more vulnerable to climate change changes. And for total organic carbon, this was the proportion of organic soils. And then we used existing risk factor parameter relationships. So we needed some way of relating climate variables to the risk of the parameter increasing or changing. So for total organic carbon, we were to use an existing peat bog degradation model. And these were all combined to give us a parameter uplift factor. And we were able to spatially see how that would vary across the country using UK climate change, local projections, and other geospatial data on the catchment and source characteristics. And then finally, the final step was using historic data for that particular parameter. So historic for example, in this example, organic carbon data, we were able to project how we might see increases in that parameter in the future. Each parameter we were interested in, we had a different approach. So for example, I gave you an example previously of what we did for total organic carbon, but for algal taste and odor, we used a model to relate air temperature to surface water temperature in a lock. And then we were able to determine for each of our water sources whether we would reach this tipping point. And this was combined with existing information on nutrient risk in the catchment. So we were able to essentially identify whether a lock would be, a reservoir would be at risk of a future algal bloom and future taste and odor issues. And this allowed us to identify those sources which would be a greater risk of change in the future, and able to show how the different climate change scenarios we're looking at would influence risk. In general, when we're looking at the distribution curve of the concentrations for each parameter, we were predicting increasing maximum concentrations, and that the distribution curve would essentially move further right, meaning that the 95th percentile values of the present day would become more common in the future. The final step of the project was to assess how the predicted changes would impact on water treatment processes themselves. And Scottish Water has already developed a set of mass balance models for each of its 229 water treatment works, and these provided us with an excellent tool for testing the new raw water quality envelopes that we developed in the previous phase of the project. And so far, climate change predictions have been fed into 57 of these models. So these models essentially allow us to test whether a treatment process becomes stressed or less capable if we provide it with differing inputs in terms of the raw water that we receive. And through this, we were able to identify the key processes that would be at risk. And not surprisingly, the processes most at risk, as we are seeing increasing organic carbon, would be coagulation processes and the result in solids load onto solids removal processes, in particular rapid gravity filters. We were also able to identify those works that didn't have existing processes for dealing with both either dissolved manganese or taste and odor. And in his presentation, Richard went through the types of processes that would need to be deployed in those circumstances. There is now the potential to test the climate change predictions in the models for the remaining 229 sites, which would obviously give us a lot more information on what works, the capability of the works, and what adaptation measures would be required. So that was really quite a quick tour of what was 18 months of work, and I just got a final slide to summarize what we have found to date. So climate change is expected to significantly impact upon raw water quality in both the 2050 and 2080 horizons. Without adaptation, most of the Scottish water sources will have a risk of deteriorating water quality by 2050. Reservoir sources from our analysis seem to be at greatest risk, and they will become increasingly vulnerable to greater organic concentrations, temperature changes, and risk of manganese and algal issues. And really finally, I'd like to sort of stress that the work we did only represents really a starting point. And I think both organisations recognise that more research and monitoring is needed to understand what is obviously quite complex relationships between climate change and environmental processes and raw water quality, and that we need to bridge the gap between academic research and practical methodologies that can be applied by those who are working in the water industry. Okay, thank you for listening. Hand you back to Duncan.
Thank you very much, Tim, and great to see how some of the principles that Richard set out are playing out in practice for Scottish Water. So we're going to hand over to Peter Rook now we've got about 10 minutes for Q&A.
Cool. Thanks for that, Duncan. So first question I think is for Tim, and it's farming is necessary for a sustainable food chain. Sorry, just my Q&A flashed off for a second. Yeah, farming is necessary for a sustainable food chain. With a growing population, there is a larger demand on food production. With the changes in weather patterns, sorry, my seam's just playing up. With changes in weather patterns and, as mentioned, high usage of fertilizers, there'll be more pollutants entering rivers and lakes. On a grand scale, what do you think would be the way forward to avoid these nutrients and pollutants from entering waterways from farmlands? Oh, I think you're on mute there, Tim.
Yeah, that's an incredibly broad question, Peter. And I think others who work in the sphere of how to manage farmland inputs and catchment measures would be a better place to answer that. I mean, clearly in our project, we identified that if nutrients are available, then we see an increased risk of algae and algal taste and odor in the future. So we obviously need to consider, I guess, our best practice in terms of farming practices as much as possible. And we recognise in our work, Peter, one thing we didn't consider is future land use changes and how farming practices might change and might move around in different and occur in different parts of the country. And that's definitely something we would like to look at in the future.
And definitely something with new development as well that will be how our land use changes over time. Elliot, Murray, Richard, do any of you have any thoughts on that?
I'd probably kind of add to what Tim said. There is, I think, most of the water companies for their catchments that have farming in them, they do have discussions with the farming bodies and organisations and work together to try and kind of find some balance between the needs of the farmers and the needs of protecting the water catchment. Where we can, they may be kind of try to move to more sustainable uses or alternative products that are less of an issue, but at the same time, it is a risk that just needs to be managed and somehow addressed, whether that's changes for the farmers or additional treatment for the treatment works.
Brilliant. Thanks, Richard. All right, so if we move on to the next question, and I think it's more directed towards Elliot and Murray, what kind of MIB concentrations are we likely to see in the future? We saw unprecedented raw concentrations of 84 micrograms per litre last year, which was extremely difficult to treat. Is this common throughout the UK?
I think that's probably addressed at me and Richard, that comment.
I think so, yeah.
Okay.
Thank you.
I wouldn't like to put a number on where they're going to go to. 84 is high, but yeah, that is kind of the site I referred to, which had to use both powdered and granular activated carbon. That had started in the last 5 years, maybe, seeing levels at that kind of level. And to put it in perspective, to avoid taste and odor problems, you need to get it below 2 for 2 MIB and below about 5 for Jasmine in nanograms per litre. So yeah, that is a challenge, and I think we are going to see certainly more areas reach those values and maybe a few places get higher. But yeah, that's a challenge that I think is continually being looked at.
As I just add to that, what Richard said, Peter, I mean, as part of our work, we were looking at the risk of an algal bloom occurring in a reservoir. We haven't got to the point yet of quantifying what that might mean in terms of a concentration. But what we did find through the literature review and the studies that we looked at is that cyanobacteria, which are the culprits for MIB in Jasmine and taste and odor problems, are more likely, the more likely type of algae to occur as we get warmer waters and issues with stratification and nutrients as Richard and myself talked through. So that, that could lead to a greater occurrence of MIB and Josmin. And as Richard said, the human taste threshold for these compounds is extremely low, 2 and 5 nanograms a litre.
Yeah.
So if we're seeing concentrations, 20 and above in a source, we're going to start to need to think about dedicated treatment processes.
Brilliant. Thanks, Tim and Richard. So I think we have time for one or two more. And the next question is a bit of an open question. In your opinions, what are still the significant barriers for more widespread application of nature-based solutions in the UK for catchment water resource protection? Probably actually a little bit more tied into last week's, but so if no one particularly feels comfortable answering that, I can move on.
Yeah, the nature-based solutions aren't something that I have much expertise in, the actual solutions and what prevents them. My involvement tends to be, I design the treatment work solutions that are used to compare the costs of the two. And the nature-based solutions always come out cheaper. There may be an element of risk because in that reluctance, because you're designing a treatment works to cope with it, as opposed to putting in solutions and then not changing the works when you don't know what's going to come down. But yeah.
Cool. Thanks, Richard. And probably the last one. Are our reservoirs in locations where there may be an increased risk of saline intrusion during higher tides and sea levels? If so, this may complicate the effects of stratification. So I don't know who wants to have a go at that one, or anyone knows that.
I can only say that most of the ones that I've dealt with have been upland reservoirs, so they're well above sea level. I'm not aware of any at low levels. It tends to be deeper reservoirs where you get stratification. So
yeah,
I
tropical
would
islands.
imagine there's many, but
Yeah,
I
could add to that, Peter. Obviously, in Scotland, most of our reservoirs are quite significantly above sea level. Maybe that's different in other parts of the country or other parts of the world. But one thing I did mention in our presentation is we start our project with a risk assessment, and we identified these key parameters. But we did also look at a whole other set of potential climate risks. And one thing we did consider was the impact of saline intrusion on boreholes that are possibly close or more in lower areas or closer to the coast. So that is one potential risk of climate change going forward.
All right, thanks both. I think that's probably all we've got time for today, but we can make an attempt sort of. Oh, sorry, Murray, you've got your hand up.
Very quickly, thank you. There was a question which I did say I'd answer live, which I could have answered by typing, but anyway, does it account for precipitation rates? I think that was a question from Sonia with relation to Red Up. The answer is yes, it accounts for precipitation rates because the rainfall goes in with a very fine resolution precipitation rates, and we perturb that with the same resolution when it comes out. So that's the quick answer to that question.
Thanks, Murray. And I think, Barbara, we are going to see if we can try and answer some of those questions later on. Just we don't have much more time. So I will hand over to Duncan, who will wrap this up.
Brilliant. Thanks, Peter. And thank you to all our speakers, both from today and the previous 3 webinars as well. It's been a great journey through the sort of science of climate adaptation in the water industry. So just a few words about forthcoming events. First over to Hannah to talk about CIWEM events.
Thanks, Duncan. So a couple of updates on forthcoming events. Next week, there is a free webinar you can attend held between the CIWEM presidential team and the presidents of the Association of Directors of Environment Planning and Transportation. So you can sign up for that on the CIWEM website. Also next Friday, CIWEM Rivers and Coastal Group Technical Conference in London. Exciting news, drum roll. So the CIWEM Presidential Conference on the 8th of April 2025 is now live booking, so I'm really excited about that. Hopefully see you all in Coventry. And just a plug for the National Flood and Coast Conference in June in Telford. Thank you.
and some British Hydrological Society events to mention, particularly one coming up on the 21st of May. It's a one-day national conference about flash flooding, organised jointly with the Royal Meteorological Society, and that's going to be held at the Royal Geographical Society headquarters in London. So look out on our website, hydrology.org.uk, for information soon about booking. And you can see some other meetings coming up a bit further into the future. Regional meetings in particular I want to mention. So BHS regions are being revived after some rather quiet periods in some cases, and several of the regions I know, including Pennines, which covers the north of England, and also Wales and South West, are planning meetings over the next few months. And they'll all be advertised via the BHS website, via social media, and also our emailing list that anybody can join. So that is it. Thank you so much for listening to this webinar and possibly the previous 3 as well, and hope to see you sometime in the future.